Hello students, so in this lecture we are going to discuss about some of the mathematical expressions which is used in characterizing a sensor. Like we will first start with something called transfer function. Transfer function. Now, we know that whenever there is a stimulus, a physical stimulus, which is say represented by this small s, this stimulus, we get an output from the center, from the sensor, which let's say which is electrical output, that is capital S. Now these two are related to each other, but there may be different ways by which stimulus is related to the output. Like if we have a case of unidimensional case, that is we require only one sensing stimulus, or the stimulus comes only one time, then we call it as a unidimensional function, and in that case we can represent the output s as equal to a linear function, that is a plus ln sorry a plus b into s. This is for a unidimensional function. Which means we are getting which means we are getting only one stimulus. Now, in this case, in this equation, this is actually equation of a straight line with an intercept and a slope. So this initial value, this value, this a value, this is actually the output when there is no input. It corresponds to the output for zero input. Whereas this b, which is the slope, it is actually the sensitivity of the sensor. dVt. Now the thing is that all the sensors may not be unidirectional, may not be linear functions. There can be other sensors also which are not there may not be a linear function of the stimulus and the output, like logarithmic sensor, where the output is equal to a plus b ln s. It can be exponential also, that is s is equal to e to the power a e to the power ks or we can also say that s is equal to 1 by k ln small s by a, or it can be even a power function, that is s is equal to a0 plus a1 s to the power k. So there are many options. Now, so this is how the output of a sensor is can be related to the input of a sensor. Now, so this is the transfer function. Now, the second aspect of sensing is another parameter which needs to be known is something called a full scale input. Or FSI. Full scale input. Full scale input is the difference between the maximum and the minimum output stimulus that is achieved. So we can have a small s, which is the maximum physical input received by the sensor, and you can have a small s minimum physical input which can be received by the sensor. So these two are related. Then the ratio 1 decibel is equal to 20 log S max by S min. This is the full scale input. So similar to this full scale input, we can also have a full scale output, FSO, full scale output. It actually indicated different from full scale input. It is not that difference between the output. It is actually the changes between the maximum and the minimum values of electrical outputs when maximum and minimum input signals are applied. So if S max is providing an output say S1, which may not be capital S max, and S min is providing an output S capital S2, then the difference between the two is called the full scale output. Now, third is the accuracy. Accuracy means we need to find out the error. So there are two types of error. The first one is called the absolute error. Absolute error, and it is given as the measured value minus the true value. One might ask, how can we know what is the true value? Now, the true value is actually calculated by taking a large number of measurements and then averaging it. So average of large number of outputs. That's how we can put it. Now, another type of error which is important is called the relative error. The relative error is nothing but the ratio of the absolute value or absolute error divided by the true value. This is the relative error and represented as again the mean value minus true value divided by the true value. This is the relative error, RE. Now, there are many sensors available, but to get the best possible sensor with optimal value accuracy, the sensor needs to be calibrated first. So, calibration is important. So, the fifth one parameter to characterize a sensor is the calibration. Calibration. Now, it is basically an adjustment or a set of adjustments made on a sensor or a device to make that device functional and error free. So, in order to get in order to get a constant value in the equations with good accuracy, the linear transfer function, which has been calculated as let's say gamma is equal to a plus bp. So we are using the same equation but with different parameters. So this here, this is the output, gamma is the output, and p, this p is the input. Previously it was being represented by capital S and small s. Now it's gamma and p. Now the a and b constants need to be found out for calibration, to have a good calibration. Now what is really obtained after a lot of calculation is that this b value, that is the sensitivity of the sensor, can be expressed as gamma 1 minus gamma 2 divided by p1 minus p2. This is basically the slope, and a, which is the output at 0 input, it is nothing but simply gamma 1 minus b into p1. So the pressure of calibration, the term called the pressure of calibration, can again be expressed as P, which is equal to gamma minus A divided by B. So the calibration error is actually a type of inaccuracy which is accepted by the manufacturers. Right. So the next aspect for a tensor is hysteresis. Hysteresis error is the difference between the two outputs value that correspond to the same input, depending on the direction followed by the sensor. Okay, so if we have, say, the sensor output in the y-axis, and the reference point pressure on the y-axis, then the hysteresis plot may look like this. Okay. So this is actually with an increasing pressure we get two values, and this is for the decreasing pressure. Now nonlinearity, as we have previously mentioned, all the sensors may not be linear. There are some sensors which is nonlinear. Now the linear function is a sensor is calculated by maximum deviation of the straight line. Now this again now the total nonlinearity, if there exists total nonlinearity, is the difference between the intercept value of y and x. So we can express, if there is a nonlinearity, say sensor output and pressure or the stimulus are like this. Instead of going like this, it is like this, not be linear. So in that case, we need to find out first the midpoint in the x-axis, which say we represented it by xm, and so this midpoint is actually the maximum of x minus the minimum of x divided by 2 plus the minimum of x. So this gives the midpoint of x, and the line connecting the endpoints represent the total amount of nonlinearity, which calculate as the percentage linearity. So if we have something, say here the percentage linearity is equal to S max, output max, minus S min by 2 plus S min, midpoint of the y region, and divided by minus the true value or the output at a particular input divided by this midpoint of the x region. So this gives the linearity or percentage linearity. Okay, now in this case, if this ys is the actual value of y at this value of x, and if the actual measured y value passes through 0, then we can say that the percentage linearity is equal to S max, or it's actually S sometimes, S max by 2 minus ST divided by SS divided by S max by 2 into 100%.